when you say parallax, what does that mean? Sorry.
Yeah, so you can it's a way of determining distance, and the reason we have two eyes is there's a baseline between our eyes, right? So if something is close to us, when you look at it with one eye and then the other eye, its apparent relative position shifts, right? And the closer it is, its apparent position shifts more. So there's a relationship between how far away something is and how its relative position shifts as you look at it from two different viewpoints. So we have two eyes because it gives us depth perception, and you can do a really cool trick with kids, right? Put a patch over their eye and ask them to catch a ball. It's actually really tricky. You have to concentrate a lot at it because you have to use a lot more information about the trajectory of that ball because you're missing the depth, right? So what you can do on Earth is you can put a telescope at the top of the Earth, a telescope at the bottom of the Earth, and you can use that as your two eyes. And if you're looking at Venus and you've got the background of the sun, you can basically look at how close Venus is by how different its position looks against the background of the sun. Now, to do that, this is really interesting, right? To get to other parts of the Earth, you need to have a navy, right? You need to be a country that says, I want to know how big the solar system is. And to do that, I need you, Captain Cook, to sail halfway around the world and set up an observatory and make an observation at the same time we're making that observation in England.
Okay.
Right? And so the Greeks knew how big the Earth was 2,000 years ago. They also knew how far away the moon was 2,000 years ago. But it wasn't only until about 300 or 400 years ago that we actually knew the size of the solar system, how far it is to the sun. And so technology is involved again there. You don't just need a telescope. You need to be able to navigate to a certain point on the Earth in a ship, right? So you need to be you can tell why England did it, right? Because back then we were pretty awesome with the Navy. Right.
Yeah.
Anyway, what were we talking about?
We were actually talking about. The initial question was to do with the sun and how we know.
Yeah, the mass of the sun. So once you know the distance to the sun and how long it takes the Earth to go around the sun, you can calculate the mass of the sun. Yeah.
And then from that, how do we know what it's made of?
Right. So it can't be made of wood. It can't be just a lump of wood that's burning. It can't be made of coal. Because there's too much stuff there. It would have a lot more mass if it was doing that. So it can be made of gas, and it can be made of hydrogen gas. And so the volume and the mass of it means that it can be a whole bunch of hydrogen gas. And then we know by looking at it we know its temperature as well, because we can see what color it is. Right. Here's another thing, right, that people frequently misunderstand, right, because of the taps in England, right? The hot tap is red, the cold tap is blue, right? But the bottom of a flame is blue where it's hottest. So actually in the universe, hot things are blue. But really, the taps are backwards.
Yeah. It's true. I mean, I guess that's more the what do you call it? The danger thing, right? Red is like psychologically more dangerous.
Right.
Right.
Absolutely. Yeah, I totally get that. Yeah, but it's not physics, right?
Well, yeah, of course, because also like light, ultraviolet is more dangerous than infrared, I guess.
Yeah, it's higher energy. Yeah, it's much higher energy. Yeah.
Okay, cool. So that kind of fills in those things.
And then, of course, we can actually build another instrument and point it at the sun and see that there's hydrogen there from spectrographs. And so when you look at the rainbow of the sun, there's actually missing parts that correlate with the wavelengths.
So when you say spectrographs, what does that do?
So a raindrop through refraction creates the rainbow effect. It breaks up light into its component wavelengths, right? And the reason it does that is in optics, when you go from one medium into another medium, there's a bend of the light, right? It's either a refraction or a reflection. And so you have an angle of incidence, and then you have a refraction angle and a reflection angle. And that angle is actually dependent on the wavelength of the light. So shorter wavelengths get bent more than longer wavelengths. So as light passes through a droplet of rain, the light actually gets broken out into its wavelengths because of refraction through water. Now you can do that with glass as well. If you get a glass and you shape it appropriately, right, into a prism, and then you've got a very nice album cover, you can you can have light come in one side and break it out into the components of wavelength on the other side. So you can actually put one of those on a telescope, and you can break up light from our own sun. Actually, you don't need a telescope to do that from our own sun. You just need to be able to look at that rainbow very, very closely. And so there's a German physicist called Fraunhofer who did this, and he noted that there were missing parts of the rainbow when he looked at it in detail in his lab. And so when you look at the solar spectrum, you'll hear the term Fraunhofer lines, and they're to do with the presence of chemical elements. And so the chemical elements that are present in our sun show up in the rainbow of our own sun. And so you can see the hydrogen and the helium. You can see the hydrogen and the helium, and then you can see other things as well, the things that we're made of, right? So you can actually see magnesium and calcium and iron in the sun, the things that we find here on Earth. And so now you've got an observation that shows, well, the stuff that we see in the sun, some of that's here on Earth as well. So now you start to think, well, maybe the sun and the Earth formed at the same time from the same stuff. Yeah.
Interesting.